Welcome everybody in this beautiful Jacobs Hall, if you have not been here, in this beautiful winter morning in Berkeley. I'm here to introduce Vivek, who's about to finish his PhD. Vivek joined from Caltech, and then it's been, there's a story that says you learn as much from your students than vice versa, and it hasn't been truer than Vivek's case. I believe Jim will agree that it's not only that there was this vast amount of knowledge in Vivek, he also made sure that both Jim and I understood what he's been doing with meticulously prepared slides every single week we have met. And so thank you for that. And I remember writing the CSGF recommendation letter, and he didn't have a lot of publications by then. It was just the first year, but it was clear that both the personality traits as well as the intellectual skills were there. So it's been one of the easiest letters I have written. He's run our CS267 in such a way that probably was the easiest year that we have run that class as the lead TA, and he deservedly got a outstanding TA award for that. And I don't know, it's been a pleasure to having you. You ran your own collaborations, found them, sustained them. It's been exemplary. So we're looking forward to having you give your last talk as a PhD student.
Sounds great. Thank you so much. Thank you to everyone who showed up in person. It means a lot. And thank you to everyone online as well. Hopefully you can hear. Let's get started. So I'm going to get right into the content, which is linear algebra forms the backbone of today's scientific computing and ML models. It's so essential that we benchmark our supercomputers against each other by the rate at which they solve large linear systems of equations. To wit, today, Lawrence Livermore's El Capitan supercomputer can do 1.7 billion floating point operations per second, as measured on the LinPack benchmark. So it's very clear that the compute we have at our disposal is truly vast. But a growing number of applications today rely not on linear algebra, but multilinear algebra. And I'm going to define what that is in just a second, but first I'd like to take us on a tour of three seemingly disparate applications that really showcase what we might be capable of, and then I'll tie these three things together with a common thread. So what can we do with our 1.7 exaflops of compute? Well, scientists of late have invested very heavily into foundation models and machine learning interatomic potentials for chemistry problems. So today, scientists can use neural networks to do in silico simulations of atomic configurations. The idea is that given some configuration of atoms in space, you'd like to predict some properties, for example, energy, charge density, the forces on each atom. And if you do this both accurate and if you do this fast, you could really discover brand new classes of materials or drugs. We're clever enough about these models that we can even bake in physical laws like energy conservation, or the one we're going to talk about today, like symmetry, directly into the model structure. For example, if I have a molecule and I predict that the energy of that molecule is some number, and if I rotate that molecule in space 180 degrees, my model will actually predict exactly the same value. So that's really nice. Let's look at the second application in our zoo. Now consider this large 3D array that's filled with these data points. And in this case, that array is filled with data points that contain data from an Amazon review tensor. So a tensor is a generalization of a matrix in 2 dimensions, or a vector in a single dimension to 3+ dimensions. And each point in that large array basically indicates that some user reviewed some product and used some particular word in that review. So just given the pattern of non-zero elements and the values of those non-zero elements, there's very few values that are actually non-zero in this large array. I don't actually need to know anything about the products or the users or even the words that they're using. I can extract patterns and do data mining with this data set just based on these patterns. And this is an application called sparse tensor decomposition. And we'll talk a little bit more about this in the second half of this talk. And the last application that I want to talk about, it's more future work, kind of an emerging technology. So this is an emerging technique to do biomedical imaging. So for example, if you've got an infant or a toddler who may not be inclined to sit still in an MRI machine, You can instead tape electrodes to their head, which apply very weak and harmless currents to actually measure the interior tissue structure. And this is a demo on an orange. And turns out the kernel that's required to solve this is just a bunch of linear least squares problems. And I think this is future work, but we'll talk about this. So this is a zoo of seemingly random problems. What is the linking thread for all of these? Well, it turns out that all three of those applications rely on this primitive called the multilinear map. The idea is that I've got this 3D array, A, and that's going to interact with vectors x and vectors y that come in to produce a bunch of vectors z through this very simple linear equation. It's just a summation over these indices of a, x, and y. So it's very simple. And in reality, for a lot of these applications, I don't have just one pair of XY inputs that come in. I've got lots of pairs of inputs that come in. So I've got this large set of inputs, and I want to produce a large set of outputs. When I get to that point, this kernel is known as the matricized tensor times Cauchy-Rao product. It's a bit of a mouthful, but I'll explain a little bit more in just a second. The idea is that if we accelerate that primitive on the left-hand side, we get a variety of gains in all these downstream applications. It's the engine that powers them. It helps a little bit to fall back to linear algebra, some primitives that many of you in this room may be more familiar with before we get to this MTT-KRP, this strange kernel. Consider a linear map. That's a function of one vector that produces another vector output that has this additivity and multiplicative property in its argument. We can ask ourselves, for this linear map, what is the fundamental kernel or a highly optimized operation on a computer that lets us implement such maps efficiently? And the answer is matrix vector multiply if you've got a single input, and matrix matrix multiply if you've got multiple inputs. And matrix matrix multiply today is one of the most optimized primitives on modern CPUs and GPUs. Okay, you may be familiar with this standard matrix matrix multiply. Let's go one step further. Now suppose that we've got a function that it has two arguments, x and y. What is the corresponding fundamental operation that lets us evaluate this map efficiently? Well, it's going to be matrix vector multiply again. But now, instead of just taking x, I take the Kronecker product. That's this outer product of all elements of x against all elements of y. And then I multiply that against this short wide matrix A that's encoding the map structure. So that's that diagram on the top left there. And again, if true efficiency comes when I've got a large batch of inputs, so when I've got many XY pairs, I now take not a Kronecker product, but this column-wise Kronecker product that you can see here, this sort of parallel array of operations. And that particular operation is called the Cauchy-Rao product. It was first defined in 1968 in a very different context than what we'll be studying today. If I take that short wide matrix A and I reshape it, just take its values and kind of fold it up into a 3D object, I get the tensor. And that's the connection between these two formulations. So that's what I want to do. I want to take this operation, A times X Cauchy-Rao product Y, and all I want to do is optimize this. I've hopefully convinced you at this point that this is something that we want to optimize. There's lots of applications that depend on it, but there's lots of challenges as well. One of the biggest challenges that face any operation that deals with tensors, these multidimensional arrays, is the so-called cursive dimensionality. It's this umbrella term that's used in a variety of contexts that just means that things get hard when we deal with things that have lots of dimensions. And specifically, a lot of tensors that we're going to deal with, in fact, every tensor in this presentation is going to be sparse. That means that most of the values in that tensor are going to be zero. And if you've got a tensor, for example, this tensor containing data from Reddit, it may have a non-zero density as low as 10 to the negative 10th. That is extremely low, and that makes these tensors sort of unwieldy and very difficult to compute with. The computational efficiency is very low. As well, notice that in that formulation I showed you earlier, we've got this Kronecker product that we have to take if you do implement this map naively. And the problem is the height of this Kronecker product is exponential in the number of objects you're working with. And so in some cases, we just won't be able to materialize this. We're going to need some more clever strategy to deal with this. And finally, it's the fact it remains that most existing algorithms and software, they target matrices, not tensors. There's emerging work that targets tensors, and there's been a lot of prior work, but perhaps this is a more underdeveloped area. And that's what this dissertation aims to address. So we are going to accelerate this MGTKRP primitive in those first two applications that I showed you earlier. We're going to show something like an order of magnitude speedup for the best existing implementations using low-level kernel engineering. And then we're also going to turn to a more theoretical contribution and offer asymptotic speedups through new randomized algorithm theory. That's the program for today. And I'd like to get started with our first application. So we're going to be discussing two research papers today. The first one is going to be talking about optimizing these chemistry foundation models. The second one is on tensor decomposition. And I'll briefly mention these other three papers that we did over the past 5 years, but we're just not going to get a chance to talk about today. So chemistry foundation models. This is going to be optimizing a primitive called the Klebsch-Gordon tensor product. I'll talk about this in just a second, but let's return to the more general problem. So given a configuration of atoms in space, so I've got their 3D coordinates as well as some metadata. This is an oxygen. This is a hydrogen. What I want to do is I want to predict some properties about this system. And in this presentation, we're going to predict the total energy of the atomic configuration. And we also want to predict the forces on each atom. If I get the forces on each atom, I can feed this to a numerical integrator, feed this to a simulator like LAMMPS, and then I can predict some properties of the whole system as some quantity of interest. Now, traditional techniques like density functional theory are very good at this, but they tend to be very slow. Physicists have used them for years. Fortunately, we've realized that deep neural networks are very good universal function approximators. So that's exactly what we're going to do. We're going to take our atomic configuration and encode it into a graph that contains nodes and edges. It's a nearest neighbors graph. We're going to feed that to a deep graph neural network that's going to predict the quantities of interest for us. Okay, that's the model we're going to use. And I don't want to just use any model. I want our model to obey certain physical constraints. A brief primer on message passing graph neural networks, if you're not familiar. What these graph neural networks do is for every node in this graph, which corresponds to an atom in my simulation, they're going to generate a small piece of data. That's this dense feature vector. I also generate a little piece of data for every edge that connects nodes. And this graph neural network is going to combine the node and edge features in some way, and then it's going to take this combined piece of data and sum it across the neighborhood of each node. And do this several layers over and over again, rinse and repeat. That's the process. The property that I want to enforce is called O3 equivariance. Essentially, if the input rotates, the output energy prediction stays exactly the same, and the forces rotate in a compatible manner. In order to do this, I need to combine the piece of data at each node with the piece of data at each edge in a highly prescriptive manner. And I've kind of illustrated this with a little cube you can see there. Let's actually zoom in and see what that operation is that I need to enforce this property. That operation is called the Klebsch-Gordon tensor product. I take my node feature X, my edge feature Y, and I interact them with this 3D block sparse tensor containing Klebsch-Gordon coefficients. These are apparently used to combine angular momentum vectors in physics. And then I finally take the output of that operation and multiply this by a trainable weight matrix W that's also highly structured to produce my output vector Z that is summed and aggregated across the neighborhood of each node. And of course, I need to do this not just for one pair of inputs, I need to do this for every single edge in the graph. And there's my multilinear map / MGTKRP structure. I end up contracting this 3D tensor against many pairs of input vectors. And here I've just written out that same matrix times Kronecker product formulation. Now, what's the problem here? Well, as I said, our GPUs are optimized for dense matrix multiply. They're certainly not optimized for this. Our GPU can be running at less than 10% utilization, and this operation can be taking more than 80% of the model runtime if you implement this naively. So we need to optimize this. And here are our contributions. We introduced this kernel generator, open equivariance, and this is joint work with Austin Glover, who's sitting in the back there, that's got something like an order of magnitude speed up over the best open source codes for this problem. That's the E3NN package. And it performs on par with the 4.0 version of NVIDIA co-equivariance. We were sort of faster of the 0.2.0 version, but they've since caught up. And there's a closed source kernel package. And there's lots of optimizations that I'm going to talk about. This is sort of the software stack. Users interact with our kernels through Python and PyTorch. We do the hard work of compiling these kernels, building them, and dispatching them to the hardware. Okay, So I want to talk a little bit about these 3 bullet points, the idea that we exploited sparse structure, we used techniques from flash tension, which is this kernel generation strategy for LLMs. We did a lot of kernel fusion. I'm going to dive into each of these points in a little bit more detail in the next few slides. So let's talk about that. This work has several potential applications. So we are now sort of officially integrated into NQUIP and Mace. So if you would like to, are in the space and you want to use these kernels, you can just take your YAML file that configures these things and just say enable open equivariance. And you can use these kernels that we've built without any additional difficulty on your part. So we accelerate NQUIP, the Mace foundation model, as well as diffdoc, which is this molecular docking code. We haven't gotten integrated into that middle one yet. But we accelerate the kernels for it. Let's go a little bit deeper into that CG tensor product. Let's look at the structure of that 3D array that I showed you earlier. So the idea here is that there's more structure than I showed you on that last slide. Many of those tiny blue blocks floating around in that cube have identical structure. They repeat over and over again. And we know exactly the structure of that tensor as soon as the user says, I want this model. So what we can do is we can very naturally split this large operation into a series of what I'm going to call subkernels. So each of those subkernels deals with one of those small blocks that are floating around in that cube. It's going to contract some segment of X with some segment of Y to produce some segment of the output. And you can see here on the bottom left that I've illustrated what exactly is the non-zero pattern in each of those blocks. These are the Klebsch-Gordon coefficients. They have a very regular pattern and fairly low non-zero density, anywhere from 20%. And as you increase the size of these blocks, it gets lower and lower and lower. So that's what I'm going to do. I'm going to break this operation up into a sequence of little steps, one for each of those blocks. And now in a single slide, let me illustrate what our optimizations are. Recall here that we need to execute millions of these operations, one for every edge of the graph. So what I'm going to do is I'm going to take each of those XY pairs, and I'm going to distribute them one at a time to a GPU warp. So a primer on a GPU architecture, the GPU consists of lots of little execution units. These are these tiny little vector units that perform computation in lockstep. So what I'm going to do is I'm going to distribute one batch element to each warp that can allow us to operate in a completely asynchronous manner. In other words, I have very little synchronization overhead between different warps if I pick this strategy. And it simplifies the design of my kernel generator immensely. Okay, that's great. Let's now zoom in to see what it takes to execute one of those operations on one warp. So let's zoom in one more time, and now we run into another problem. Because these warps are operating completely asynchronously, they've only got a limited pool of SRAM or fast memory that they can compute with. So what I'm going to do is I'm going to generate a schedule for the computation in Python. It looks something like this. I'm going to load some subsegments of X, Y, and my weight matrix W into the fast shared memory, or SRAM. I'm going to do some computation. I'm going to flush the outputs to the global memory. I'm going to rinse and repeat. And this allows us to not only minimize the global to shared memory traffic, but it also allows us to shepherd carefully that limited pool of memory that we have. So that's great. Let's zoom in one more time and look at what exactly it takes to execute one of those small tensor contractions. Well, at this point, I should mention that the side lengths of these blocks are very small. Typically, they're less than 10 on a side. At this point, I can fit the segments of X and Y that correspond to that block entirely within the fastest memory that the GPU has to offer, and that's the GPU register file. By sticking all my operands in the GPU register file, I can unroll the sequence of operations that's inside this sparse tensor contraction. And basically, the GPU code that I generate, that's the PTX or GPU assembly code, just consists of a long sequence of multiplications, fuse, multiply, adds. It's just arithmetic, and that's about as efficient as it gets. So in one slide, this is sort of a sampler of all our optimizations. It looks complicated, but if you look at what the kernel actually looks at the bottom-most level, it's a very simple algorithm, which is take a single block that corresponds to the subkernel, loop over all ijk coordinates and the value at that coordinate, and then you just perform 2 multiplications and an addition to the output. That's a single update equation, and what our kernel generator does is it uses just-in-time compilation to fully unroll the sequence of operations in this loop. Of course, this is a machine learning model, so you can't just be content with the forward pass or calculating this operation. You also need the gradients of this operation with respect to its inputs. But this is so simple because it's just 3 update equations instead of 1, and it's so simple that we're just not going to cover it. What's more interesting about this particular operation is that I actually need higher partial derivatives for this. So here's a little fact from high school physics. Let's say that I've got my function E, which is coming from my neural network, that's predicting the energy of this molecular configuration as a function of the weights W and the atomic positions R. Then the derivative of E with respect to the atomic positions is the force. This is a wonderful property that means that PyTorch auto-differentiation can allow us to predict the force just given a prediction of the energy. But we have a problem now, which is that ideally I want to minimize with respect to the weights W the difference between the predicted force and the ground truth force that I get from some DFT simulation. And it shouldn't surprise you too much that if I'm optimizing a first derivative, which is my force, a second derivative pops out when I try to optimize this. So there in the bottom right corner, I've got the second partial of energy with respect to R and with respect to W. The good news here is that PyTorch is happy to do this. It doesn't care. It will calculate arbitrary higher partial derivatives if and only if you supply a quote unquote double backward pass to the CG tensor product. We need to differentiate through the derivative itself. At first, this can seem very dispiriting. You can say to yourself, well, we spent all this time engineering the forward pass, the backward pass. We went from 1 update equation to 3. Is the implementation complexity just going to keep spiraling? I don't want to do this anymore. Frankly, in our paper, we show that you don't have to do this anymore. We show that just using a combination of the existing forward and backward pass kernels, we can just take linear combinations of the forward pass and backward pass, and that gives me my relevant derivatives. And this just follows from the linearity of this operation and just writing the chain rule out several times. Specifically, I call backward 4 times, the forward pass TP 3 times. I add these things up, and those are my derivatives. We verified this numerically, and you can take it on faith that this is the identity. The last optimization that I'd really like to cover today is this technique called kernel fusion. So our GPUs are most efficient when they're not shuttling data back and forth from global memory to SRAM. Notice that this tensor product operation is really running in the context of a graph convolution, combining a node feature with an edge feature and taking the aggregate result and summing it across the neighborhood of each node. Well, that pattern has a memory access pattern that is very similar to sparse times dense matrix multiplication. And that's something that HPC researchers, many of whom are in this room, have studied extensively. So here on the right, I've shown a way that we can fuse one classic algorithm for SPMM, this fix-up-based SPMM algorithm, with the CG tensor product. The only relevant lines in this sort of morass here are this first one, which executes that subkernel sequence. That's exactly the same as earlier. And then the idea is we only write to the global memory when our warp crosses a boundary of the adjacency matrix. It's a pretty standard technique, and that lets us save a lot of global memory. That's a sampler of the optimizations that I want to cover today. I now want to get to the results. So let's look at the throughput of this kernel, the forward and backward pass in multiple precisions, float 32 and float 64. And throughput is on the y-axis, so higher is better. I plotted here the throughput for several configurations from these chemistry foundation models, several tensor products. In green is our kernels. Blue is the open source code E3NN, and yellow is the 040 version of NVIDIA's coequivariance package. And you'll see here that in many cases, we're holding our own against this closed source package, and in other cases, we're showing an advantage. And both of these packages are just significantly faster than E3NN. And this is really offering us something like a 5 to 6 times end-to-end speedup when we plug it into the foundation model. So that's really nice. And these experiments were conducted on the NVIDIA A100 nodes at Lawrence Berkeley Lab. These trends hold across multiple GPU architectures. So we also tried this, so you can run this on pretty much any NVIDIA or AMD GPU. We tried this on the A100, the A5000, which is an NVIDIA budget board, and we also tried this on the MI250X, which is on OLCF Frontier, which was at some point the fastest supercomputer in the US. And we can see here that we consistently offer those order of magnitude speed up. We can ask ourselves, okay, I've shown you a bunch of numbers. I'm saying, okay, we're several times faster than E3NN. I want to ask, are we really using the machine to its full capability? We're taking advantage of our full potential. That's what this roofline plot measures. On the x-axis here, I've got the arithmetic intensity. That's the number of floating point operations per byte moved of data for several different problem configurations. And on the y-axis, I've got throughput. The idea here is that I want to be as close to the top of this plot as possible. And I've got this dotted line there that's showing what is the theoretical maximum that I've computed for this problem. You can see here that our kernels and covariance, the latest version, are very close to the so-called roofline, which means we're making very good use of the memory bandwidth available to us. And this red is sort of an earlier version of covariance that, again, has been improved. Finally, let's tie this together and put this into a foundation model, which is MACE. So here on the y-axis is the simulation speed and megatime steps per day. For our kernels, those are the sort of green bars on the left here, covariance, multiple versions, and E3 and the open source code. So here we're, again, offering 5 to 6 times end-to-end speed up. Here, covariance is actually faster. It's got a faster simulation speed, but this is partially because they've optimized some kernels that are very specific to this foundation model. If you look at the kernel runtime breakdown, the kernel that we're optimizing, which is this CTP kernel, Clebsch-Gordon tensor product, that runtime in blue is very similar across these different implementations. So we're happy with this. The takeaway here is that we achieve state-of-the-art performance, and again, this great end-to-end speedup while remaining open source for this particular Clebsch-Gordon tensor product. And the key point here is we really exploited all of that structure that was latent inside the tensor to achieve these gains. Graph neural networks, by the way, have a lot of applications, and we have some additional work on GNNs for a very different context that explores different kernels in the Clebsch-Gordon tensor product. And you can see the references in this presentation for that. That's this IPDPS paper. But I want to pause briefly for a couple of minutes at the conclusion of this section before we talk about our next problem and consider a much more general setting. So any questions briefly, either online or here? Nothing is fine. That means I've been clear. Okay, I think we should move on to the next section of this talk then. And if there are any questions, feel free to interrupt. Okay, I now want to consider this setting where I've got something like this array full of Amazon reviews that are this large, multidimensional, sparse array of data. And what I want to do is I want to take each axis of this array and I want to assign a dense vector to it. If I do this, the interpretation of that task is that I'm representing this large array using a sum of outer products. This is very similar to the matrix principal component analysis, just extended to higher dimensions. Instead of representing a matrix as a sum of 2D outer products, I'm representing a tensor approximately as the sum of 3D outer products. I collect these outer products into these so-called factor matrices, U1, U2, and U3, and this generalized vector of singular values, sigma. So that's the task. And from this set of factor matrices, I can extract patterns, do data mining, clustering, do whatever I want with this. Now, it turns out that there are no really good polynomial time algorithms to do this tensor decomposition task. We'll have to settle for some heuristic. And the heuristic that we're going to use is alternating least squares. The idea is that I will initialize each of those arrays, U1, U2, and U3, randomly. I'm going to keep all but one array constant, and I'm going to optimize the remaining value by solving some problem. Okay, I hope the program is clear. This is an alternating factorization approach that is kind of classic in machine learning. It's just going to be much harder for tensors than it is for matrices. So let's look at that in a little bit more detail. Let's say that I keep every matrix but uj constant, and I want to optimize for the optimal value of uj. What is the problem that I need to solve to do this? Well, it's a linear least squares problem where I minimize over uj, where the design matrix of this linear least squares problem is a Cauchy-Rao product. And the right-hand side, or the observation matrix, is a flattened version of that tensor that I showed you on that last slide. I take that tensor and I flatten it into a matrix. I've illustrated that problem on the left, and if I actually solve that problem using the normal equations on the right, you can see that this MGTKRP primitive pops out again. I've got this large short wide matrix that is, in this case, very sparse, that's being multiplied against this Cauchy-Rao problem. And this is the bottleneck step in this solve. That tensor can have billions of non-zero values. Every value requires an interaction between a row of the Cauchy-Rao product and a row of the output. And that's the operation that I want to speed up. Notice something else here. I don't have any structure in the tensor here that I can exploit. Earlier, I had all these repeating patterns. I knew the structure fully ahead of time. Indeed, the task here is to discover structure in the tensor. So what do? I don't have any structure in the tensor, but I do have a lot of structure in that Cauchy-Rao product that I can exploit. So here's how I'm going to solve the problem. I've got a lot of columns in my major size tensor. I've got a lot of rows in this Cauchy-Rao product. I'm just going to randomly sample some of those rows, form a smaller system of equations, and then solve that. Simple enough. And all that technique relies on this field called randomized linear algebra. The algorithm, to get a little bit more formal, that we're going to apply is called sketch and solve. I'm going to apply a short wide matrix S to both A and B, and that's really going to cut down the row count of this problem significantly. Now I've got a much smaller problem. I solved this cheaper problem, and ideally I want the solution that my cheaper problem produces to have a residual that's very close to the true minimum residual. That's this epsilon delta guarantee. With very high probability, the residual that my approximate solution produces isn't too bad. It's within 1 plus epsilon of the true minimum. And as I said, we're just going to randomly sample j rows of A and B to form much smaller matrices. And this technique is very popular in machine learning. And here are our main contributions. We're going to build a data structure that's got this runtime that's logarithmic in the height of the Cauchy-Rao product and quadratic in the column count to draw samples from this very tall matrix. And it's going to sample from a particular distribution called the statistical leverage score distribution on the rows of that Cauchy-Rao product. And when we plug this into our solver, it's going to yield an algorithm that's got lower asymptotic runtime in terms of n, the dimension of the tensor, r, the target rank, and I, which is the side length of the tensor, to achieve that epsilon delta guarantee that I showed you earlier. This is a really efficient algorithm, both in theory and in practice, that I'll show. So I briefly teased that we're going to sample randomly, but not uniformly from this long matrix. How do I do this, and what is this leverage score distribution? Let me give you some intuition. Let's say that I asked you, yes, you, in this room, to fit a line to this set of data. This line must pass through the origin, and you must fit it to all of these 10,000 data points. How would you do it? I really hope that you wouldn't take out a calculator and start computing and do the math and do all of that. That's probably not the best way to do this. In reality, you'd probably just pick a subset of these points, say, yeah, that looks about right, and draw a line through it. That intuition can be formalized, and we can just take a subset of these points to perform the fitting. The only question is, which points do we take? And here again, our intuition tells us that points that are further out along the x-axis have the most influence on the solution, so we should take those. That's what this concept of statistical leverage scores formalizes. So let's let this matrix A have this singular value decomposition, this reduced SVD, U sigma V transpose. I'm going to define the ith row leverage score as the squared row norm of the ith row group, where U is coming from that SVD. What this leverage score quantifies is how much influence a particular row has on the solution. So if I sample according to these most influential rows, I'm guaranteed that my solution quality is good in terms of the residual. This theorem is basically saying that if I sample according to these leverage scores using my sketching matrix, then with a number of samples j that is something like r, the target rank, times 1 over epsilon delta, those two quantities I showed you earlier, we achieve the guarantee that we want. Okay, simple enough. This seems like the magic bullet for our problems, except not really at all. Because let's take a typical problem configuration. I, the side length of the tensor, can be something like 10 million. I may be dealing with a three-dimensional Cauchy-Rao product. This matrix A is going to have 10 to the 21 rows. I can't even index this with a 64-bit integer. So there's no way that we can actually form this Cauchy-Rao product, take the singular value decomposition. This is clearly not a workable strategy. Instead, I'm going to employ this technique called implicit sampling. Let's imagine each of my matrices that form the Cauchy-Rao product as this array of cards. What I'm going to do is I'm going to draw one card from every stack, take the Hadamard product or element-wise product of all the vectors written on those cards, and that's my row from the Cauchy-Rao products. So let's let these random variables, HADAS1 through HADASN, jointly follow the leverage score distribution. These are random variables for each card that I'm drawing from each stack. And what's really nice here is that I can write down exactly what that conditional distribution is in a closed form. Let's say I want to get the probability that I draw row S3 from matrix U3. Well, I take the Hadamard product or element-wise product of the rows that I've already drawn from U1 and U2. That's that green vector over there. I take this sort of complicated element-wise product with the Gram matrices of things I have yet to sample from with the Gram matrix of the whole Cauchy-Rao product, pseudo-inverse, form this G greater than K matrix. And then I take the S3th row of U3. I take the outer product of this green vector and the blue vector against itself to form a matrix. I take the element-wise product of all three quantities in these angle brackets, and I add up all the values. And that's a number that gives the probability weight. So this diagram looks a little complicated, but it's just showing you what the major players are in this equation. So that's great. I've now written down the relevant probability distribution in a closed form. The problem here is that actually sampling from that is still very expensive. I would need to calculate 10 million values of that probability distribution for every single sample that I'm taking, and that's clearly not workable when I need to take 65K samples and spend more than 10 million operations to materialize that probability distribution. So here's the key hack that we're going to use to solve this. So let's assume that I magically give you that distribution Q on that earlier slide. I just hand it to you. How would you sample from that distribution? This is a classic programming interview problem. If you're just given a probability distribution, how do you draw a sample from it? Well, the answer is pretty simple. I initialize sort of an array of bins, and the jth bin has width qj. And then I toss a ball into these bins, represented by this random real number in the 0 to 1 interval. And I find the bin that my ball landed in, and that's a draw from this distribution. And that equation there is just telling you that this is the particular bin j that my ball landed in. I find that bin using a binary search. Classic technique. I can visualize that search as a walk down a binary tree. This binary tree, I'm going to truncate it to log I over R levels. At the root, I branch right if the sum of the probability mass in one branch of the tree is less than my ball that I've thrown, and I branch left otherwise, and I keep doing this until I hit a leaf. The key here is that we can compute the summation of those qj values much faster than we can actually materialize all those individual qj values. And so here's the one slide of math that I want to make you kind of suffer through. Let's say that I allow a particular node to correspond to this interval, S of v through E of v, and I sum up all the qj values in that interval. Well, that summation just goes straight into that inner product that I showed you earlier, and I can pre-compute these matrices G of v that store some cached information at every node. I can calculate this matrix G of v for each node in time IR squared for this whole tree, and storage space is linear in the size of the input, and it's very efficient because I use glossary operations. Now when I want to sample, now with the internal nodes, all I need to do is calculate this little operation that I have up there in very limited amount of time, order R squared. I read the normalization constant off the root, and then I keep going down the tree, and at the leaves I spend a little bit more time, but you can get that down. When the dust settles, the complexity to draw each sample is just nr squared log I, summed over all the modes of the tensor, and that's very efficient. So that's a little overview of the algorithm we're going to use. And finally, we've drawn efficient samples from our leverage score distribution, and now I want to get to the results. Let's first talk about how well this sketch preserves the geometry of the column space. So the idea is that if I start with a set of orthonormal vectors, they should remain orthonormal in the transform space. So let's define this D of SA quantity as the condition number of SQ. That's the sketched matrix minus 1. So higher is basically more distortion. The column space is not being preserved. You can see here that green, our sampler, has very low unnormalized distortion compared to the competition. This product approximation of the leverage scores increases that kappa of SQ minus 1 value significantly by multiple orders of magnitude. As we increase the number of matrices, we're taking the Cauchy-Rao product up. And on the right here, you can see what happens is we increase the column count of this Cauchy-Rao product while keeping the sample count constant. And in this case, both samplers increase their distortion, but ours increasing it by a lot less. So that's very good. So let's actually plug this into the downstream task, which is randomized tensor decomposition. So you can see here that I've got the target rank on the x-axis. So this is the number of columns that I'm using for my outer products. And the y-axis is accuracy or fit. You can see here that this competing algorithm, CP-ARLS-LEV, it's a very efficient product approximation, but it degrades its accuracy as the target rank increases because it's an approximation. Whereas our algorithm, STSCP, achieves very close to the fit of non-randomized ALS, even at very high target ranks, something like 125. Now, there is one sort of missing dimension to this, which is that our sampler is more complicated, and therefore it might be slower. But we show here in this plot that for a lot of tensors, we not only achieve higher final accuracy, but we also make typically faster progress to the solution. The x-axis here is update time. So this is progress of the algorithm, and the y-axis here is accuracy. You can see here that green, our STSCP algorithm, is achieving very high fit, and it sort of lies above the envelope of all of these CP-ARLS curves for different sample counts, which basically means that we're making faster progress to the solution. So the takeaways here is that we combined a lot of techniques, theoretical techniques, to build this sampler for the Cauchy-Rao product that operates on structures that have got trillions of rows, that really effectively preserves the column space geometry and offers this order of magnitude sample efficiency boost over these state-of-the-art baseline methods. What's more, our data structures rely on these very optimized BLAS2 and BLAS3 operations, symmetric rank K updates, matrix vector multiplies, so we can just plug into some BLAS library, cuBLAS, or anything like that, and we can really get efficient implementations. And so compare this to part one. In part one, we exploited all these properties of the tensor. Now we exploit properties of this Cauchy-Rao product. There's two extensions I want to talk about before we get to the conclusions of this talk, and that is, well, we showed the results earlier for a single node. What happens when we take this algorithm, as well as that competing algorithm, CP-ARLS-LEV, and put it on thousands of cores of Perlmutter? Well, we can see here that we get an algorithm that makes very fast progress to the solution, even compared to highly optimized, non-randomized ALS implementations. So here on the right, I've plotted the progress to solution for our randomized methods on 512 CPU cores, and I've also plotted the progress for SPLAT, which is this non-randomized algorithm. And so we are achieving nearly the same fit in a fraction of the time that taking. So more than 1,200 seconds to get like 100% of the fit. We're getting 99.9% of that in like less than 200 seconds. And to do this, we optimize both communication among different nodes and cores, as well as computation in multiple parts of the solver. The second optimization I want to talk about is that you can really apply this theoretical machinery that's used to sketch this one specific tensor product in very different contexts. So some of you on this call may be familiar with matrix product states. These are structures that arise in quantum physics. And the idea is that when this matrix product state is in a very specific canonical form, we can sketch matricizations of these chord chains very efficiently. In fact, we can use exactly the same data structure to do this. This is a nice extension of our previous results, and this is a NeurIPS 2024 paper. And the last thing I want to talk about in relation to these linear least squares problems is that last application that I showed you about, the orange with the electrodes taped to it. It turns out that 2D electrical impedance tomography, that's the formal name, requires us to solve this linear least squares problem that doesn't involve a Cauchy-Rao product, but a sum of multiple Cauchy-Rao products. And this is a particular setting where our leverage sketch needs to be adapted. It doesn't work out of the box, so you've got the sum of two Cauchy-Rao products, not a single one. But other types of sketches, oblivious sketches, will work, certainly. What's a more interesting problem related to this is, where do you place the electrodes along the boundary to extract the maximum information for some irregular geometry? And I think that's a problem that's related to sensor placement. You can solve this through something like volume maximization, these alternating heuristics. I think that's a really cool problem that I leave to future work. We don't discuss it too much. Okay, I think I should start wrapping up here. So this whole talk really focused on a single kernel. That's this multilinear map MTTKRP. But notice how much we covered. We started with instruction level parallelism, maximizing fine-grained GPU kernel engineering. We used techniques from randomized algorithms. We did distributed memory communication analysis when we distributed our algorithm to thousands of CPU cores. We explored a variety of parallel computing motifs. Dense gem, sparse matrix multiplication, even particle simulation and molecular dynamics makes an appearance here. And we accelerated this wide swath of applications. So that's a lot of mileage. I think this is proving the claim that sustained attention to some of these off the beaten path kernels yield a lot of fruit across the computation stack. So I've really enjoyed my time studying these tensor kernels. And so where to go from here? If we visualize computer science very crudely as this line, where the bottom is the chip foundry and the top is sort of theory, and this sort of orange blob shows the probability mass of current work, I see a couple of directions that I see myself going in the future. One is going up the stack. So how do we co-design new models, for example, machine learning interatomic potential models, that exploit the accelerated primitives that people are developing? I think this is a very fruitful area of study. And we can also think about going down the stack. Instead of doing this backbreaking kernel engineering manually, how do we use tools like MLIR to deliver high performance, crucially without sacrificing flexibility or expressivity or speed? I don't really know which direction I'm going to take after this, but I'm excited for every direction of this branch. There's so much that needs acceleration in this world, and I'm ready for it. So with that, I think that concludes the technical portion of this talk. I want to pause briefly and ask if there are any questions online or in person before we get to the most important portion of this presentation, frankly. So let's pause and ask if there's any questions. Going once, going twice. Okay, and feel free to email and reach out. Okay, it's clearly taken a village, and I'm very thankful to everyone who's helped. First of all, thank you to everyone who showed up today, both online and in person. It just means a lot that you would come in, suffer through all this technical content with relatively little payoff. So I hope that it was at least interesting and that you learned something from this. So first of all, thank you to everyone who showed up. With that said, I need to single out some people by name, and we will start with my advisors, Jim and Aiden. Jim and Aiden, I'm still surprised a little bit that I was accepted to Berkeley because my recommender list had no one in HPC. I sort of applied cold without knowing who they were really. And I'm very grateful because they've given me literally hundreds of hours of their time. I totaled it up. And I've wanted for absolutely nothing as a graduate student. And I feel like that's a very rare thing. So thank you very much for that.
And you found photos with similar color combinations.
Yes. As well, I also need to thank Michael, who's here, and Kathy, who's online, for taking time out of their very busy schedules to help me with multiple parts of this PhD, from my prelim exam to my qualifying exam to right here. I know that you guys have a lot of commitments, so thank you for the feedback and seminars, and especially Kathy hired me the first summer that I was here, so thank you for that. This research would not have been possible without the help of many collaborators who are in this room today. So Russell Austin, Laura Gregory, Riley, Guillaume, and Beheshta, thank you all so much, the collaborators on our shared works. And a very special thanks to Osman, who really poured a lot of time into our shared projects, both teaching and really editing. As well, it's been very nice to share this experience with so many people from Bebop and Passion. Thank you to Ben, Alok, Julia, who shepherded me through prelim to qual to dissertation. This is the end. You're seeing it. And as well, there are so many other grad students, Roger, Tianyu, Gabe, Yan Sheng. I wish you very productive careers. It's been really nice. And there are some others. I really wouldn't be here without a lot of interest taken in me by people from Caltech, where I did my undergrad. Chris, Rose, and Mikhail were wonderful undergraduate mentors, and Adam Scheffer's class on discrete mathematics still inspires and kind of awes me today. So I'm very appreciative of that. And Federico at NVIDIA was a wonderful mentor. So thank you to him as well. There are so many people from the CSGF program here. There's just too many to name, but Muncie is here in person, and I know there's a lot more people on Zoom. So thank you all. The highlight of my year has been going to DC and really listening to the talks and going to the poster sessions and learning everything that. There's a few more people that I need to thank especially. Many of them are on this call. Allison, Ananth, Lily, Emily, and Daniel supported every decision that I made leading up to grad school, and he supported every decision that I made in grad school. So thank you so much for all of that. The last and most important acknowledgement goes to my family. My parents and my brother are in the audience today. My brother is starting his first day at Scale AI, so say congratulations to him. And these are some pictures through the years. I bear a lot of gratitude for the support that long precedes this project, runs through it, and likely support that follows this as well. So with that, I will say that's the end. Thank you. there aren't any questions, I'll be sticking around. Please take coffee, fruit, all of that stuff, and please feel free to talk to me. Thanks so much, and thank you to everyone online.